The last two sections of Chapter 6 goes over some counting principles that, um, aside from Venn diagrams, I mean, which will still show up here and there, will also allow you to, make counts of possibilities a lot, which again kind of factors into what will eventually become probabilities. And the first of which is called the multiplication principle. Now, as we go through this, we're gonna learn a number of formulas that work under certain circumstances, but they are by no means going to be representing every circumstance you may face. And they do expect that there's some that, by logic, you'll know what to do under those circumstances. Whether it's just like multiplying a number a certain number of times and things like that. So, that will be part of the challenge as well, because some of this is kind of assumed that some certain circumstances, basic circumstances, already. So, the multiplication principle basically states that if I know that there are, m certain ways of performing task 1 and n certain ways of performing task 2, then if I want to know how many possible ways that the two tasks can be done together, or task 1 followed by task 2, that would be m times n. The generalized principle basically states, that if there's, no matter how many of these things come along, that if I know how many different ways or different ways of doing a certain thing is done, then and if I have a number of these things and I want to figure out how much is going to be, how many different ways I could combinations of ways I could do them together, I would just simply multiply those numbers together. It sounds more complicated. It's kind of hard to put into an abstract idea, but let's have a look at a specific example, for instance. So example 1, a female executive selecting her wardrobe purchased 2 blazers, 4 blouses, and 3 skirts in coordinating colors. So basically, they can be mixed and matched in any combination and not look odd. Okay. How many ensembles consisting of a blazer, a blouse, and a skirt can she create from this collection? So take a moment and think about how this could be done based off of what that multiplication principle basically stated. Okay, so basically, the number of ensembles that we can make comes from the number of blazers times the number of blouses times the number of skirts, because there's 4 possibilities or 2 possibilities of blazers. So there'd be 2 outcomes from that. There'd be 4 outcomes for the number or possible blouses that could be chosen, and there's going to be 3 outcomes for the skirts. So if I simply say, okay, if I take 2 times 4 times 3, there would be 24 different combinations that she could wear this collection into the office for her work. So another example, 2 soups, 5 entrees, and 3 desserts are listed on the special menu at the Neptune restaurant. How many different selections consisting of 1 soup, 1 entree, and 1 dessert can a customer choose from this menu? So take a moment and come up with how many different meals selections that could be done. So again, really, I mean, it comes down to the number of selections would be the number of soups times the number of entrees times the number of desserts. So that'd be 2 times 5 times 3, which would mean there's 30 different meals that could be here. Now, so far, I mean, what we're looking at is that, we're only taking 1 from each category, and it starts getting more complicated. Maybe you would go to a restaurant and, if you had side dishes, you could have 2 sides, or you could have, soup or a salad, but then there's 2 soups, but there's 5 salads, so then you have those kind of things playing a role, and it's like, okay, what do I do with these circumstances? So, we're going to get into those as we move along with this. But keep in mind that right now we're just basically saying, okay, we have these categories. We're selecting one from each category. So how many different combinations can we come up with? Now we start getting into some of the questions that I'm talking about here. A rolling combination 4-digit padlock is unlocked by moving each of 4 rollers so that as to produce the correct sequence. Each roller has 10 digits. You can assume 0 through 9. How many possible combinations are there? And how many combinations are possible if no digits are repeated? So if you know that no digits are repeated, how much fewer basically combinations do you actually now have as a total? So take a moment and determine how many possible combinations there are and how many you would have if there were no repeats allowed. Okay, so how many possible combinations are there? Well, if I have 4 rollers, each could be any one of 10 different digits, then the number of combinations would simply be 10 times 10 times 10 times 10, or 10 to the 4th power, and that would give me 10,000 different combinations that could be, that it could be. Now, if you were to be given a condition that the digits can't repeat, well, then it comes down to be a little bit different here, because if they're not allowed to be repeated, then the first number in the sequence could be any one of the 9 digits. The second one, well, I have only 8 that have not been used before, and I can only pick out of 8. And then same thing with the next one. I only have 7 left over, or 10, 9. I think I skipped 9. Yes. So the number of combinations are going to be 10 times 9 times 8 times 7, which is 5,040. So you're talking about 4,960 less different possible combinations. That makes the possibility of picking the combination. It's still very difficult, but it's much more probable than if you had all 10,000 combinations. So the last part deals with permutations and combinations. And I want to put a disclaimer out there first. Sometimes you're going to see they'll use the word combination in for like an English vernacular, but the instance they're describing is actually a permutation, and we're going to learn the difference between the two. So don't get mixed up between the word combination. They say how many combinations of this can happen, or how many combinations of that can happen. Don't automatically assume it's a combination. It could also be a permutation. So what's the difference between the two in reality, as far as mathematical terms? Permutations is if you're given a set of distinct objects, so they have to be all different things. A permutation of the set is an arrangement of these objects in a definite order. So, if I'm told that, I'm going to pick from these 5 people to have 3 different, positions on a team. And one's going to be the leader, one's going to be the programmer, one's going to be some other role. Now, if I say Tom's going to be the leader, Jane's going to be the person who does the coding, and the Jake is going to be the engineer or whatever. It's going to be different if I say, okay, well now Tom's going to be the engineer. Jane's going to be the leader, and Jake's going to be the engineer. It's a different combination. So the order does matter in that kind of case, because whatever I name first is the leader, whatever I name second is going to be the programmer, coder, and the third one's going to be the engineer, whatever it is. So that's what a permutation is. Basically, it's like the order in which I pick, or the order in which these people or things are filling the slots matters. So now they do talk about a factorial. A factorial, you'll see it as a symbol as an exclamation point. Basically, A factorial means that you're going to take a number and multiply it to every integer that's beneath it until you get to 1. So if I do 7 factorial, that's 7 times 6 times 5 times 4 times 3 times 2 times 1. 0 factorial is assumed to be 1. And that's the way these are defined. So don't read them as like you're really excited. If you see a 7 with an exclamation point, this is like you're saying 7. It's 7 factorial. And you can see the factorials are used in the formula for a permutation. So the number of permutations of n distinct objects taken r at a time. So if I have like 5 things, I'm going to choose 3 of them. N would be 5, R would be 3. And I'd plug it into this formula, n factorial over n minus r factorial. So let's have a look at a for instance. So you're given the digits 1, 2, 5, and 7. And you want to arrange them into 3-digit numbers. So you're only going to choose 3 out of the 4 digits you have. They want to know how many 3-digit numbers can be made with these four digits here. So I know in this case n is 4. I'm going to choose 3, so that's r. So I'm going to do the permutation of 4 comma 3. So that's going to be 4 factorial over 4 minus 3 factorial, which is 24. So basically, if I use 1, 2, 5, and 7, there's 24 possible 3-digit numbers I can make from those 4 numbers. And in this case, the order matters because if I say 1,200, or if I say 125, it's going to be different if I say 215. They're different, so it does matter. Now, that's a permutation. That formula is for a permutation where I have, everything is distinct. Those digits were all different, okay? If I have a situation where some of the digits would have been the same, I would have to use a different formula. And so basically here, if they're not all distinct, then I would use this formula here, where basically the number of permutations would be based off of me saying, okay, n factorial over n1 factorial, n2 factorial. So it depends on how many groups I have that repeat. So for instance here, I want you to try example 2. How many different signals can be made by hoisting 2 yellow flags, 4 green flags, and 3 red flags on a ship's mast at the same time? So here, each yellow flag is going to look the same. So those really don't matter which order there are. So, you have 2 that are in the group for yellow flags, 4 in the group of green flags, 3 in the group of red flags. That means you have a grand total of 9 flags. So out of those 9 flags, how many different ways can they be raised to produce a different sequence of colors is what you're looking for here. So take a moment, see if you can come up with an answer to it. So this is a prime example of something that would be used, with this particular formula. If I want to look for how many different combinations of signals I can make, I have 9 flags total, so the overall n is 9. I called n sub y for yellow is 2, n sub g is 4, and sub r is 3. And so when I want to figure out how many different signals, it's going to be n factorial over ny factorial times ng factorial times nr factorial. So it's going to be 9 factorial over 2 factorial times 4 factorial times 3 factorial. When I work that out, I get 1,260 different signals. So, you have basically 1,260 different messages that could be created, and as long as you know what those combinations of flags represent, you could communicate certain things that are going on the boat based off of the way those flags are raised. A combination, on the other hand, is basically an arrangement where the order does not matter. So if I just say I'm picking 3 people out of 5 to do this project, but they're not assuming any particular role, then me saying I'm picking Tom, Jane, and Eric is the same as me saying I'm picking Eric, Tom, and Jane. It doesn't matter because no one's fulfilling a different specific role. Whereas if I actually assign them roles and say, okay, well, Eric's going to be the leader, and Jake's going to be this, and Jane's going to be that, and if I change, okay, well, no, let's let Eric be this, and let Jane be the leader. That's a different. So, um, so combinations, the order does not matter. So if it says here, like in example 3, in how many ways can a supermarket chain select 3 out of 12 possible sites for the construction of new supermarkets? So for instance, if they say, I'm going to choose Pittsburgh, Philadelphia, and Harrisburg, does it matter if they say that or say, I'm going to choose Harrisburg, Philadelphia, and Pittsburgh? No, it doesn't. It's the same 3 cities. It doesn't matter. If they wanted to say which one's going to be the corporate headquarters, which one's going to be, the distribution center, and which one's going to be whatever else, just a regular supermarket, then that would of course have a change and an effect, and that would be more of a permutation. So this is a combination. Work out the combination, and we'll check it in with you in a second. So now let's look through this. So as I said, it is a combination. We know we have 12 in total. We're selecting 3 out of. So n is 12, r is 3. And using the formula, it's going to be 12 factorial over 3 factorial times 12 minus 3 factorial. Which, and I always remember the combination one because, the numbers that I have on the bottom should total 12. So when I see the 3 and the 9, that makes sense. So 12 factorial over 3 factorial times 9 factorial. And that would be 220 different combinations of 3 new locations of supermarkets. So now for these last few examples, you're going to make a decision about what's the best way to approach this. So example 4 here, a student is giving a reading list of 10 books from which he must select 2 for an outside reading requirement. In how many ways can he make his selections? So take a moment, figure out ways that you could possibly deal with this, and we'll go through it. All right, so in this one here, now first of all, we're going to assume he can't choose the same book twice because, I think most people would be on to him on that one. He has to pick 2 out of a list of 10, so he can't say, I'm going to pick this one, and I like it so much I'm going to pick it again. You have to do the outside reading assignment. You need 2 separate books. We're going to assume that. So we could just do it. We say, okay, well, there's 10 books, n is 10, r equals 2, and we're assuming no repeats. Now, the other thing we have to consider here, does the order matter? So if he reads like The Last of the Mohicans and War and Peace, those are 2 big books. Does it matter if he reads War and Peace first and Last of the Mohicans second, or does he read Last of the Mohicans first and War and Peace second? No, in the end, he's reading the same 2 books, so it really doesn't matter. So we know that the selection order doesn't really matter for this. So this stands to be a reason for combination. So I can set it up just like this and say, okay, if I do 10 factorial over 2 factorial times 8 factorial, I would get 45 different 2-book selections. Now, a lot of people have a tendency sometimes to confuse this situation and say, well, then I shouldn't I be able to do 10 books, then 9 books after that, and get like 10 times 9 and 90. There seems to be a logical reason to it, but when you're doing that, you're assuming that you're picking them in a particular order. In this case, you're not. You're not picking them in a particular order. So, if you're doing 10 times 9 and saying 90, that's because you're also saying, okay, if I reverse the order, it matters somehow, and it really doesn't. So that's why there's only 45 different 2-book selections you could have here, because the other way would count some of those more than once. And the last example, a space shuttle crew consists of a shuttle commander, a pilot, 3 engineers, a scientist, and a civilian. The shuttle commander and pilot are to be chosen from 8 candidates, the 3 engineers from 12 candidates, the scientist from 5 candidates, and the civilian from 2 candidates. So basically, there's 8 people. Usually because the commander and the pilot have to know how to fly the shuttle. So they're all going to be pilots, and those are 8 candidates. One will be called the commander, one will be a pilot. So there's going to be 2 picked from that group. From the rest, you're going to pick 3 engineers from the engineer group. You're going to pick 1 from the scientist group of 5, and you're going to pick 1 from the civilian group of 2. So how many different space shuttle crews can be formed based off of this information? So take a moment and work out the problem, and we'll go over it momentarily. Okay. So here we actually have a combination of several things. For the commander and pilot, choosing from 8 candidates, I am doing a permutation, because if I select, Colonel Smith and Colonel Jones, and I say one's the commander, one's the pilot, well, it's going to matter which I assign to which. So the order does matter. There is a certain order to the selection. For the 3 engineers, well, I just have 3 engineers. We're not saying it's a lead engineer and other things, payload engineer. I mean, sometimes they do designate like that, but we're just saying 3 engineers. So, if I select the 3 engineers, it doesn't matter which order I select them. No, if it's the same 3 people, it doesn't matter which order I name them. As far as the scientists and the civilians go, basically all I'm going to do is consider how many candidates there are, and that's going to be the possibilities for them. So when I look for the number of crews, I'm going to do a permutation with N being 8 and R being 2 for the commander-pilot candidates. I'm going to multiply to that the engineer candidates, which is going to be a combination where N is 12 and R is 3. And then I'm going to choose a scientist. Well, there's 5 candidates for that, so I'm just looking for the number of science alternatives there are. And same thing with the number of civilians. There's only 1 out of those 2 being chosen. So when I work this out, this is going to be 8 times 7. So there's 56 there. And I got that 8 times 7 because if I do the permutation and have 8 factorial over basically 6 factorial, that's going to take away all the numbers from 8 factorial except the 8 times 7. They're going to all cancel out. When I look at the combination of 12 and 3, I'm going to have 12 factorial over 3 factorial times 9 factorial. I'm going to multiply that to 5 because it's the number of scientists I have to choose from, and times 2 because that's the number of civilians I have to choose from. So when I put all this together, I get 56 times 220 times 5 times 2, which gives me 123,200 possible crews that could be for this space shuttle mission. And that's just the combinations from these people. So, just from this pure standpoint, now there's other things they would normally look to choose from candidates and things like that and put them through tests and things like that to make them qualify and all that stuff. And the reason why they do all that is because there are so many different possibilities, and that's why if you're chosen to be an astronaut on a mission, whether you're a civilian or a scientist or whatever, it's a very rare thing. So that's all I have for this. If you have any further questions, please make sure to bring them up in class. Until next time, have a good day.